then. All right. Good afternoon, everyone. Welcome to the second lecture in COMP1521. Welcome to anyone who's joined the course late as well. There is a recording of Tuesday. You've missed one lecture. There is a recording of that linked to the class webpage. You should have email from me with a link to that webpage. All lectures will get pushed up to that webpage. Sometimes it might take a little while after the lecture, but of course you've got the link to the lecture in your email. I'll send you an email, or well, actually no, I'll probably switch to just using announcements from the course forum. So make sure you join our lovely course forum. Again, thanks to Jashank for setting up this course, which provides a very nice course forum experience. So we have Tute Labs starting this week. There was some last minute chaos, but we got tutors, we got classes, we got everything happening for the first Tute Labs yesterday. This week is just revision C. There's all sorts of chaos in week one. There are students still joining the course and so on. So we're not putting any new content in this week's Tute Lab, just giving people a chance to revise their C. And there are one or two things that are mentioned in the Tute Lab that didn't actually get covered in COMP1521 or COMP191 perhaps, so it's your chance to catch up on things. And there will be a bit of this. For example, we'll be using for loops. So if you haven't seen for loops, you'll have to revise a little bit and understand what a for loop is. We're doing this for minor topics. There's not much difference between a for loop and a while loop. But feel free to ask your tutor about that and to explain that. So another topic that came up is based number systems in different bases, other bases. Now, some of you have seen numbers in base 7 and converted numbers in base 7 to base 9 and things like this. It's actually, yeah, it's quite enjoyable sort of arithmetic things. But we're leaving you to familiarize yourself with that. So we looked at converting between base 10. The crucial bases for this course are bases 10, 16 and 2. So by hand you should be able to convert between those bases and understand what's happening. Now it gets a bit tedious if the numbers are large, but at least for small numbers you should be able to do the conversions between those. And we did note one nice thing about base 2 and 16 is you could move between base 2 and 16 easily by hand, even if the numbers were large. So you can explore that in your own leisure. So we need to know about base 2 because that's what's really happening underneath us in the computer. We're going to explore operations that you can only understand in terms of base 2, in terms of binary digits, in terms of bits in this lecture. So we need to understand base 2. Base 16 is just convenient. If you write things out in base 2, the numbers are just too long. It's much more convenient to write them out base 16, where they're 4 times shorter. So for human use, we often use base 16 and put base 16 values perhaps in our C programs. All right, so recapping that. There are lots of little things there. Nothing should struggle. Some exercises that hopefully you'll work through. And then we got to the lecture. Yesterday's lecture wasn't crystal clear, but then we talked about how the bit patterns to represent in a computer positive numbers are obvious, but then the question you've got is how do I denote a number as negative? And it's not done in the first way you'd think of. The first way you'd think of would be reserve a bit to say positive or negative, and it's not actually done like that. It's actually done with a weird system called 2's complement. Oh, and my annotator is not working. I'm scribing and nothing's happening. Let me restart my annotator. I like drawing on slides. Let's see this. I can. There we go. I can scroll around 2's complement. I like doing that. 2's complement. Now, I would say, yeah, if you came away from a lecture and thought, yeah, I didn't really understand that from what Andrew was saying, but it sounded important, go online. Wikipedia has a beautiful explanation of 2's complement. There are a few nice explanations of 2's complement and things like that. We've also got some explanations of this stuff and linked them to the class webpage. So where we found nice things from lectures in past CSE courses or other universities, we've also linked them into the class webpage. So you can check out those alternate explanations. Now, you know, I've already said, oh, that's an example we're going to come to shortly. We've got, what I like is programs. I don't have to show you the program. I can just compile it. We've got a program which is show you 8 bits 2's complement. What do I call it? Just call it 8-bit. And what am I doing there? Well, typing the minus O would be good, wouldn't it? And getting the compile line right. Very clumsy today. Alright. That's a program that prints out all 256 8-bit numbers in 2's complement. If you've got 8-bit values and you're using 2's complement, these are the integers you can represent, and they turn out to be -28 to 127. So the positive ones are obvious, the negative ones are a little weird, and they're formed by getting 2 to the 8th minus the value. So for -128 we get 2 to the 8 and subtract 128 from it, right down to -1, where we get 2 to the 8 and subtract 1 from it. Why? Yeah, well, it's not for human use. This is confusing for humans, but it's fantastic for the silicon. It simplifies the operations, lets you make them run faster, let them take a few less picoseconds or femtoseconds or whatever the appropriate, however fast your processor is. Alright, let me go back to my slide. So we saw that code. We also gave you another program. You can play with that program that will print out the bits of any in. Well, actually I can do it myself.
Picoseconds, probably.
Picoseconds just tells me it's probably the right. What we're saving by going to 2's complement versus a simpler representation. But if you multiply those picoseconds by billions of operations, it suddenly can start to matter. We'll just call this PB. Alright. So this program lets me put in an arbitrary value. Let's pick a completely random constant of 42, and it gives me the bit pattern for it. For a 32-bit number and a negative 32-bit number. Next week's tute, this will be a topic. This will be the first question I think in next week's tute will be check your understanding of this, and there'll be opportunity to ask your tutor about that. All right, leads me now then on. We've got this notion, yeah, integers are bit patterns, but they're stored as bit patterns. On screen, consider carefully the program I've put on screen, which reads a number, multiplies it by 1 billion, and then prints it out. Let me compile my program. I've called it test.c. If you want, by the way, if I've got everything, oh, it does seem to be working. Yep. I'm doing this on my home desktop, but I've got a process running that asyncs it to CSE in a directory served by a web server, so you can grab it as I change the files. You're saying, what's rsync? Well, the other thing is I'm using iNotify to detect changes. What's rsync? What's iNotify? How do I do this? Serve things up with a web server? Come and do COMP1521 with me next year, and we can talk about all of these things. All right, on screen's this program. Let's try running it. So I enter 1. It prints out 1 billion is 1 billion. You're saying, Andrew, this program would have seemed stupid back in week 1 of COMP1511 or COMP1911. Yeah, that is true. The point is a little bit different. What happens if I enter 5 here to print out 5 billion? Oh my God, DCC. I should stop saying, oh my God, I'm not an 8-year-old girl. Sorry, that's a bit sexist. Do 8-year-old boys say, "Oh my God"? I'm not sure. But anyway, let's look at the code on the screen. What has happened? DCC, the code produced by DCC said something has gone wrong at line 7. This is line 7 here. Something has gone wrong there. Now if you read the text, DTC does a superb job here of telling me what's gone wrong. This calculation here has produced the number 5 billion, but it can't be represented as an int. It's beyond the range of values that can be represented as an int. Now if you look at this is sort of comforting in one way. At least the program stopped and reliably, and you've seen an error. It's a bit worrying if this if this program was running your pacemaker, say. It might be bad if it's inside your chest, it's printing out an error message and stopping. Okay, but at least we've got an error message. Let me show you something worse here though. The C standard says if you assign to a variable a value that won't fit in it, the behavior is undefined. Anything is possible. So what happens is usually another value gets put quietly in the variable. So we'll use GCC, one of the world's most popular C compilers. We'll compile the same program. GCC won't do all the checking that DCC does. Let's run the program. Enter 5 again. And there we see the sad wrong answer. Now if you thought huge error message was bad, and there are circumstances which I've alluded to where the program stopping with an error could be bad, this is so much worse, 10 times worse. It silently gives you the wrong answer. So if we have any sort of engineers in the audience that want to go on to build bridges, highways, things like this, imagine you've got a program doing calculations for the width of the girder, the thickness of the concrete, something like this for some large important structure, and the calculation puts a value too large to fit in a variable and changes the calculation silently, and then the bridge falls down, the skyscraper falls down, whatever, the highway collapses because of a silent error like this. So there is a major concern here. That's a big thing to worry about, that with a common C implementation, if a calculation produces a value that's too big or too small, is in too large, in absolute terms either positive or negative, won't fit in the representation, it produces a silent incorrect result. Why? So part of the reason is that perhaps if you're doing calculations for a critical infrastructure or critical calculations, C integers aren't where you should be doing them perhaps. I guess you could use DCC and get the checking there, but you have to have thoughts there about where you're doing those calculations. Alright, now rather than worry about bridges falling down, let's look at the question here. So I said type in. You're thinking, alright, I want my C programs to be safe. What value is it safe there to put in an int? What I want my programs to be robust, work everywhere. I want to write great programs. What range of values is it safe to put in an int? And it turns out the C standard does tell you this. That's the good news. The bad news is I think it guarantees you can put anything up to 32,767 and negative 32,768. I think that's what the C standard says. In practice, if you're on a general purpose computer, it's much larger. But so there's a problem there in that we're not told. That limits are not very well specified. Why? All right. Little history lesson here. When C was designed,
double checked. Yeah.
Sorry, Dylan. Keep going. We seem to have lost Dylan there. All right, we may get Dylan back shortly. The C was designed a long time ago. Computers were much more diverse there in what they did with numbers. If you're designing a language like C today, you'd make different decisions because CPUs have become much more uniform in how they treat numbers. So you could make more specific assumptions without perhaps harming C. When C had to run on a very diverse set of architectures, they didn't really want to specify much in the language because they wanted C to be, people producing C compilers for each different architecture to have a lot of freedom. Don't panic. There are some things we can tell you here. But I guess one question would be, look, Andrew, why is it fixed? Why is it on this machine it's 32 bits? Why have any limit? We don't like limits. Programmers don't like limits. If you've seen malloc, one of the joys is suddenly with malloc I can create an array basically without limit, limited only by the memory I've got. So we love, rather than having a fixed size array, having an array that's just as big as needed for our task. Why do we have the limit on the number of bits in a numeric variable? And the answer is speed. We can do arithmetic much faster if we fix the number of bits in the variables. So if we can produce silicon, if it knows it's got to do calculations in exactly 32 bits, we can do the calculations much faster. There are languages that will grow the number of bits as needed. There's a massive performance penalty. It's nice for some things, not nice for others. So you can shift to those languages. We'll also see similar questions with floating point numbers, by the way. That's still to come. So if you want to have the size of your int variable grow as needed, it will run much slower. Often that's fine. They were very clear. I can give you a couple of cases where it's not fine. I can give you 3 cases where it's not fine. You're on a tiny processor that's not very fast at all, and it's got to do things in real time. That's an issue. If you're trying to process things in real time at very high speed, so you want to process radio signals or things like that, you've got incredible demands on your arithmetic. The other one would be when you had to do massive amounts of arithmetic. So if you want to do arithmetic, you want to do climate modeling or massive fields of numbers, then you've got issues as well. All right. So we're stuck with this. I've got an int, and I don't know how many bits are in it, and it's all worrying if I want to write really robust programs that work everywhere. This is one of the horrible truths we hid from you in COMP1511 and 191. What can we do about it? I've got 2 programs to show you now, which I did bring up last time. One is integer types. First I'll show you, well, this is right. The first thing is C has a lot of integer types, but they've basically all got the same problem. So I'd say don't use these basically. So in our first course we showed you char and int. There are a whole pile more types which can have more bits, or an intermediate number of bits. So short has an intermediate number of bits between int and char. Long has more, possibly more bits. Long has even more bits possibly. And if you really want to save your bits, you can go to an unsigned type that only represents the positive ranges. I'm saying don't use any of these types. You think, why the negative lesson, Andrew? Well, you will see code out there. I know that you'll be looking at resources out there, existing code out there. So you need to know these types exist. I'm saying these things exist. Yeah, don't use them in general. They're a very specific. Oh, we have Dylan back.
I checked the C standard, and it guarantees that an integer type is at least 2 bytes.
Yes.
That's it. That's the exact word. At least 2 bytes.
And you'll certainly see C compilers where it is 2 bytes if you go to tiny little embedded architectures, which is just the sort of place you might end up using C. All right. Oh, I tried to fix this and got it wrong. apparently. Yeah, alright. That's okay. Let me show you the limits. These are, on this machine, how many bits and bytes are in all the types and the minimum and maximum values. This will vary depending on where you run this program. So if you run another machine, you might see different values. How's that working? I guess there's two things. I'm getting the number of bits and bytes from size of. So that tells us how size of tells us how many bytes it takes for a type. Very handy for malloc. And I've assumed there are 8 bits in a byte, which is almost always true, and to give you the number of bits. Limits.h, you're saying, what's limits.h? Well, if you really want to know, you can say man limits.h, and we'll see if that works. Oh, come on, maybe man limits? There's no manual entry for limits.h. Disappointing. Alright. Limits.h comes with standard C compiler to tell you the limits. So it can actually tell you what's the biggest int you can have and the biggest char. Actually, I'll scroll down and show you that.
Is documented on CSC, I think.
Oh, well, don't tell me my system. My system's missing files. That's sad. All right, on the CSC system,
0p or 7p.
I don't know why, but it gives you these hash defines for the maximum minimum values for these types. All right, all this is all worries me. Oh, there is another thing here. The printf formats. There's probably questions in the chat about printf formats. These printf formats are scary. I don't really want to get into them. You can read about them if you want, but there are printf formats to handle all the possible types. No, you don't want to memorize them. No, you don't want to get a tattoo of them. Yes, you will be Googling them when you need to use them, if you ever need to use them. But they're printf's formats handling the range of numeric types isn't as pretty as we'd like by a long way. But that's not important. Right, let me show you a better program, a happier program. This one. Oh, see, this makes my heart feel much warmer, much better. These are types for you, coming to you for your programming, all your programming needs and pleasures, particularly in this course. If I know I need a certain number of bits in an integer variable, that's if. Generally, you should stick with int if you're writing just sort of generic code. But when you know you need a specific number of bits in a variable, student.h is your friend. It gives you types with ranges that are the same on every platform. Use these types, use int8 underscore t, and you get a type that can represent -128 to 127 on every last platform you run it on. Use uint32t and you get a type that goes from 0 to 4 billion and something on every platform. These types are useful, wonderful things which we'll be using regularly in this course. Because we have to do various things with bit operations, you'll be seeing these types from now on through this course. In fact, we'll be using...
Sorry, a very good question that I've seen a few times in chat. Why do we care about how many bits a type has?
Well, because we're worried that our type will overflow. We'll try and put in a value that we'll need to put in a value. During the execution of our program, our calculation will result in a value that doesn't fit in the type. And then we've either got in DCC our program stopping with runtime error, or in most C implementations, silent, undefined, incorrect, robust, bad behavior. But it gets worse. If we write a program where overflow is possible, where execution can produce a value that's too big or too negative for a type, too positive or too negative for a type, a malicious person can contrive inputs to our program to cause that overflow to happen, and then if they're deeply familiar with the internals of the workings of C implementations, can contrive that to produce executions that give them privileges that we don't want them to have. In other words, the assigning an integer value that won't fit in the variable can produce a security hole, and it ranks up there in the top 10ish sources of security holes is integer overflow of one sort or another. So that's perhaps the worst in the modern day. Cybersecurity has become such a big issue. This is one of the worst aspects of the most serious aspects, the reasons we've got to consider this the most. One thing you will see happen, by the way, is if you assign a very positive... Actually, we'll try it out with that. Where was my program, my test program? I think I can produce a negative value here. Remember, the test program just read a number and multiplied by 1 billion. So I've just compiled that. If I run it, I think if I maybe just put in 3, I'll get a negative number. Oh, sorry, DCC stops me. Thank you, DCC, but I want to run without the seatbelt here and see what happens. Put in 3. Yeah, so 3 billion is a negative number. One way a lot of security attacks happen is they do an overflow, and then of course indexing perhaps backwards out of an array or something like that to get to they contrive it to get to values they've supplied, which might exec a shell or something like this. So anyway, all right. So what now? What did I want to look at now? Oh, I will show you an instance of this, a classic bug. We still see it today. Sadly, we see it today.
I just want to say that there's something interesting about the C standard about these types is that the C standard does not guarantee that any of these types actually exist. The C standard guarantees that there's these small modifications called int 8 least t and int 16 least t. Those are guaranteed to exist, which give you at least as much space, maybe more. These exact types aren't technically guaranteed to exist, although it's very rare that they don't.
All right, so, and this is a consequence of C. We like C because it runs absolutely on anything. Any CPU out there has C for it. Well, almost any CPU. So if you get to CPUs with very limited capabilities, some of these things like int64t might be hard to do. So that is true. But for what we want, yeah. If you finish up on a platform that doesn't have these types, you're in a very special place anyway. Yeah, it's an interesting point. On screen is something we should never ever do, but we do. We've actually put there's checking in the code in this extra special checking in the code in the C checker for 1511 to try and pick this up. So I've said here C is a char variable. So what range does that guarantee? And actually, char variables are really weird. There's two possibilities, two common possibilities. One is it'll be able to represent values 0 to 255. The other is it'll be able to represent -127 to, -128 to 127. Neither of those is good here, but the behavior of the program differs dramatically. What's the problem? Well, I'd say the problem here actually goes back to naming long ago. It's probably Dennis Ritchie, who's been dead for a while, sadly. Lovely guy, but he didn't think about the name there well for getchar. Getchar really should be called getByte. I think it'd be much clearer. Well, Dennis I don't know if you had much dealings with beginner programmers anyway, but it confuses a lot of beginner programmers that getchar is called getchar. What it really does is gives you a byte. So it gives you a value 0 to 255. They're the possible values it gives you. Well, that's not quite true, is it? There's the 256 values a byte can take, and getchar has to be able to return at least one other value, which is EOF, and it has to choose another value for that. I guess it could have chosen 256, but it chose as its special value, well, actually it's not really defined, is it? It always is -1. It's hashed, but we use the hash to find EOF. So there's a special value that's not any of 0 to 255 that getchar returns to say, oh, something went wrong. Trouble here is C can only hold a certain range of values, which is possibly 0 to 255, possibly -128 to 127, but in no way is it going to end well, because whatever happens, we've got broken code. So this is a classic bug. So this is why being someone who thinks about bits can win here. If you think about bits, you think this is returning 257 possible values, this can hold 256 possible values. It just can never work. It goes, I think mathematicians proved this in about the 16th century, I think. That this is impossible. You've got a loss of information here. 257 values coming back, stored in something can hold 256. It never can work. So the correct thing here is to make that a type int. You can see why we tried to skip over this when while loops were new and scary, and bytes were new and scary in your first programming course. Let's keep moving along here.
Just one other interesting note. It actually couldn't be 256. The C specification says it must be negative. EOF must be an integer type and must be negative.
I bet there's a lot of old code out there that says something like, while it's greater than equal to 0 or something like that. Not a good idea, but I bet there's code depending on that. Yeah, alright, let me get rid of that. Okay, now, so I think we have to move on to the next. Let me just check, but I think that's everything I wanted to say about representing integers. Yes, that is. So let's move on to doing some I've got scrolled way ahead. Let me scroll backwards. Next topic, bitwise operators. So we're going to introduce a set of new operations. You've seen plus, you've seen times, you've seen multiply, you've seen divide, you've seen percent, which is more or less modulo. Now you get some new operators. You're saying, do I get an operator for power? No, you don't, sorry. C still doesn't have a power operator. There are library functions to do it for you. Here are on screen 6 new operators. Wow, 6 of them. They all work on individual bits, so they only make sense in terms of individual bits of a value. The operators are an ampersand, a vertical bar, a tilde, a caret, 2 less thans and 2 greater thans, and they AND the bits in a bitwise way. They OR the bits in this way. They invert the bits. XOR is my favorite. XOR is great. XOR is wonderful. And they shift the bits left or right. What are the good things about this? I'd say there's 2 good things about this. A, they give us a good way to manipulate the bits. We could manipulate the bits using arithmetic operations sort of indirectly in ugly ways, and that would be unpleasant, but these give us a well specified, easy to understand way to manipulate the bits. And the other thing is these operations are easy, so easy to do in Silicon. So they're like 10 times easier than arithmetic to do in silicon. So if you've got to build a chip, you look at these operations and go, I can do this. I can get a value and exclusive OR with another value. I know how to do that. It's just a handful of transistors, which means they're fast, super fast. Now, what these operations do mostly hark back to an English clergyman, I think he was. Yeah, my history's failing me. George Boole. You can head to Wikipedia for George Boole with a. That's how you spell his last name. These operations hark back to, I guess he was he the first to formalize them? The notions are much older still, but I think he was the first to really go mathematical with them. Though he wasn't necessarily talking about ones and zeros, being several hundred years before the first digital computer. So what does an AND value do? ANDing works on bits, and it's a binary operator, bits either side. If you give AND a 0 bit and a 0 bit, it gives you a 0 bit. If you give it a 1 and a 0 bit, it gives you a 0 bit. If you give it a 0 and a 1 bit, it gives you a 0 bit. Only if you give it two 1 bits does you give it a 1. Alright, so that's what an AND operator does with an individual bit. If you give an AND operator some values, it applies it to the individual bits. So an AND operator will go to these two bits and say, oh, 1 and 1, that's 1. 1 and 1, that's 1. 1 and 0, that's 0. So it does pairwise the individual bits of the values. So what do you get after you've finished an AND operator? You get the places, you get ones where both values had a 1. So you're always going to get less 1 bits in the values afterwards. Well, less than or equal to. We'll show you what an AND operation is quite useful for very, very shortly. Oh, well, here's a weird one for you. You can go away and figure this out. So you will have, this is every first year programming course by law has to have check a number as odd or even as one of the exercises you do. Actually, maybe that's not true, but you will have done this and everyone does. So that's doing it using a modulo operator to see if a number's odd. This way it does it with an AND operation. Because an odd number, the bottom bit, the least significant bit, must be a 1. And if we AND it with a 1, we throw away all the other bits. You think about it, a 1 is a 0, 0, 0, 0, 0, 0, 0, 1. And if we AND it with whatever value we've got, we're left with the last bit. Anyway, you can think about that. That might not make sense. That's one to come back to and see if you want to figure that out. And of course, the other thing you do is you can put this code in a program, put printfs around it, print out n, print out 1, print out n and 1, and see what happens. There is a question of then which should I do, by the way, and the answer is always write the code that is most obviously correct, most readable, most obviously correct. For things like this, if it's faster in the silicon to turn this into that, the compiler will do it. Modern C compilers put large amounts of effort into producing the most efficient instructions for operations. They even do really weird things. Compiler writers run gigantic searches looking for sequences of operations that are faster. So they'll check millions and millions or hundreds of millions of combinations of operations to see if they can come up with clever ones that will turn common bits of C into something faster. So
a really great question that actually just backs up your point there as well. A student asked in the chat, does n and 0 test if it's even? So it's clearly a very confusing example, given that
Does n and 0, what's anything and 0? Yeah, that's a good question. Anything x and 0 equals x. Sorry, now I've confused as well. X and 0 equals 0, always. So that won't work, yeah. So, yeah, so this code, correct? Yes, I believe so. Readable? Not so much. But it's a nice comparison for our understanding these operations. Yeah, you write the most obviously correct code.
Which one's faster, Andrew?
I'm not. I would think they'll. I'm not 100% sure, but I would think that will turn into the same code.
Correct.
If you there's a wonderful website, by the way, called Compiler Explorer. If you really want to get into this stuff, it's amazing. It shows you side by side. You can put up 2 bits of code and explore what they turn into. You have to be able to understand assembler, and we're just embarking on that journey. So, for your future, maybe. My second bitwise operator is OR. Oh, by the way, so just to, maybe you don't remember, we've heard that was Zach was that last voice, but we've got Dylan, Zach, and Jashank joining us in the lecture as usual. OR is Anne's friend, I guess you'd say. 0 or 0 is 0, but everything else is 1. 0 or 1 is 1, 1 or 0 is 1, and 1 or 1 is 1. So it gives you, if you after you pairwise apply it, it gives you a pattern which has a 1 bit if either value has a 1 bit. Very useful. The last one you really need is NOT, which inverts the bits. 1 becomes 0, 0 becomes 1. It's a unary operator, so it takes a single value. There's a nice little proof that if you've got AND, OR, and NOT, you can do anything you want, which I think dates to George Boole, in fact. So you could use those previous operations to get to an exclusive OR, but I love exclusive OR. My favorite of these operations. We'll use it much less in this course. Exclusive OR is used heavily in hashing, graphic operations, and particularly in cryptography. So exclusive OR, or XOR, 0 or 1 or 1 or 0 is 1, but 1 exclusive OR 1 is 0. So it seems like a bit little nonsensical, but it turns out it's really useful for combining 2 values without losing information. We've got I don't know if we'll get to it today, but there's an example on the class web page of using exclusive OR for a cute trick. 2 more bitwise operations. Shifting. We can shift the bits left or right. So 2 less thans send the bits left. So we can say shift the bits across 2 positions. Any bits that fall off the end are lost, and any bits on the right are 0 filled. There's a caveat there which I'll come to shortly. If you shift too far, you'll lose everything. So if you've got an 8-bit value, shifting everything 8 bits left, it's a bit stupid because you'll just finish up with zeros. Actually, no, I think that's safe. I think it's guaranteed everything's replaced by... Right shifts are generally safe, I think. It's the left shifts that are really scary. Generally, in this, always gets students in this trouble in this course if you're doing shifting of any sort, just use unsigned values. For the lab exercises where we get you to explore shifting, we'll give you code that, a template saying use an unsigned value for this. And we've already seen that, for example, if it's a 32-bit value, we'll say use uint32t. The reason is, for not particularly good reasons, which are slowly being changed in the C standard, a right shift does unpredictable things if the value is not unsigned. So, and that is a source of bugs.
I don't believe it's unpredictable. I believe it's sign extended, which is well defined.
Sign extension's not quite guaranteed, I think you'll find.
Yeah, the implementation defined.
Terrible.
Sorry, we didn't catch Zach there, but we won't go into the fine points. You're welcome to go into the fine points of the C standard and find out what is defined, what is guaranteed, and what isn't. It's I believe changing in the next C standard. But in this course, just
sorry, that's my problem. I'm reading the next C standard.
In this course, just use unsigned values when you're doing the shifts. All right, a right shift sends the bits right, and if the value is unsigned, it zero fills there. All right, so that's our operations. Oh, so I've got code now to show you the results of these operations. Where are we at? Oh, we can take a break soon. Let me see if I've got the... No, what's the code called? I've forgotten what my program's called. No, it should be called bitwise.c. Uh-oh. Bear with me. Sorry, I just haven't copied this file over to the directory where I'm working, which I'll do right now. Right, this code, yeah, it's a bit hard for us to understand. Let's not dwell on the code. Let's just run the code. So this is code you can come back to later and maybe figure out. But the program exists for us to run it and enjoy the output. So don't look at the skin. Well, call it bitwise in fact. This will let me put in any values I like and do bit operations in them. So let me put in 67, 112, and 3, and it'll do bitwise operations for those and print out the results. It's doing it, by the way, as 16 bits. Did I mention that? Maybe I didn't. Maybe I shouldn't have. So I want to do bit operations, explore bit operations with 16 bits. So there's my type, uint 16_t, which I'm getting from student.h there. Don't worry about the weird scanf, but that's the appropriate scanf to get in an uint 16t. So I enter these values. It prints out what A and B are as 16-bit numbers. You can calculate that out if you like. This 1 bit is 64, that's 2 and 1. That would be 67. It's showing us negation, flipping the bits in A, and you can see the two bit patterns. A, not A, the bits flipped, done with a tilde A there. We can see the results of doing AND OR and exclusive OR to A and B, and getting the bit patterns out. And for your cognitive pleasure, to help you understand, they're printed out in base 10 and in base 16. So you can compare the two. And if you look at this, it's actually not that hard to figure out that this is 3-3 in base 16. It's much harder to figure out it's 51 base 10. So there's a sort of when we get used to base 16, you can see it's much more compact than writing it out in base 2. And base 10 is just useless here. So trying to picture in your mind what 67 with a bit operation with 112 base 10, there's just you just have to go to base 2 to do that. All right. Now I'm going to ask if there's any good questions in the chat that I should be fielding. I can see Zach and Jashank and Abraham have been busy answering questions in the chat. But at this point, I think I'd like to take a break from talking for a little while. No, they're scanning the chat. All right, so we're going to take a 9-minute break. We'll start at 5 past the hour. So you can perhaps grab that bitwise program and compile it and play with it. That would be a good thing to do. Yeah, that'd be an excellent thing to do. Or get up, stretch, refocus your eyes, get a cup of coffee or anything like that. So we'll come back at 1:05 to continue this. Alright, welcome back everyone. Let me just turn my audio down a little high. Alright, yeah, I forgot to turn off my screen during the break, so you've seen me preparing my new next example. Alright. I'm using, on screen, is code to read in a number. It's printing it out in binary using magic code that we haven't seen yet, but it's soon not to be magic code. So we're about to reveal what's under the hood in the print bits function. But first, I want to write a program that pulls out a bit of a number. So let's run it. The program is incomplete. It's very incomplete here. Let me compile it. No, let me write it and compile it. And we'll call it third bit. Oh, why can't you type Andrew? Why? This time for sure. Let's clear my screen. Alright, we're ready to go. This is meant to print the third bit of a number. So if I enter, oh, that's perhaps a bit large, let's not overflow things. Large number. It's meant to find the third bit here. By third bit, I'm going to count this as okay. Let's make this much. Well, that worked well. Apologies for that again. Let's not get so enthusiastic. So by third bit, I'll call this the 0 bit, the 1 bit, the 2 bit. So I want to print out whether that bit is 0 or 1. Yeah, it's a bit not clear which bit I mean, but let's not. So I mean that bit, the bit position 3. Should that be the third bit? All right. Let's say we'll print out this bit here, bit position 2. We'll call that the third bit. First, second, third. Yeah, that probably makes more sense. Good sign, isn't it? You've got to be incredibly precise what you mean. So just saying the third bit, does it mean coming from the left or coming from the right? Am I counting from 0? Am I counting from 1? Yeah, good lesson. Alright, so let's say I want to print out that bit, so I'd want to print out 1 there. How do I print out that bit? It's a two-step process. Now, the first thing I've done is I've put the value in an unsigned type here, uint32. Again, there's the question of how many bits I want. I could have even gone to 64 if I wanted. But I've put in an unsigned type, and then I can do bit operations in it. What happens we'll do that separately. What happens if I get this, I get in, oh no, actually I want to put it in the type first before doing the operations, don't I? Put it there, and then I'll shift it across. I was going to do something, well, sorry, let me explain. I was going to make a common mistake. I was going to do this. Whenever you use shifts, this type here should be unsigned. What type is in? It's back up here, and it's a regular in. Don't do that. That will lead to bugs and unhappiness for you. Always make sure it's an unsigned type, which I can do by putting it there and then doing the shift like this. So it doesn't seem like much. I'll even separate that line out. But this in itself, this is an interesting operation. So I've shifted the bits right 2 positions. What does that do? We could check it's working, I guess. Yeah, why don't we check it's working as well? We'll put in a debug print bits operation and check that it's working. cumbersome, but there we go. Let me recompile that. I'll check that the shift operation really does what it's supposed to do. Let's put in a value. We'll put in a smaller value, 345. That line-up's hard to see. I hate that. Let me make them line up. I can do this just by commenting out that line, can't I? That'll get the bits lined up so we can make sure. You think, Andrew, you're being needlessly careful and pedantic. No. Being pedantic, and most times it's not desirable. When it comes to coding and bits and things like this, being pedantic is a virtue. Now, has the shift 2 positions right worked? Well, let's look at our bits. These are the bits for 345. You can verify those at your leisure. Do the conversion of that as a base 2 number to 345 base 10. But it's easy to see that the shifting 2 positions has worked. 2 zeros have come in here, and the number has come across 2 positions. That's interesting. What does that do? Is there an arithmetic analog? Let's try out some possibilities. If I enter 6, I need a bigger number, don't I? Let's enter 40. That's not the third. We're getting 10 out. Sorry. So what we're computing is not the third bit, but we're getting 10 out from a shift across of 2. If we enter 80, we get 20 from a shift across of 2. You're spotting a pattern yet? 100 is 25. Shifting right 1 position is very similar to dividing by 2. Shifting 2 positions is very similar to dividing by 4. Shifting 3, very similar to dividing by 8. It's interesting, but not what we're here for. What we want to do is get that last bit, and we can do that with another operation. We just want that bottom bit, that last bit. So let me show it as this. So let's enter 5, 6, 7, 8. So there's my 2-step plan to pulling out an individual bit from a number. I shift the bits across so the bit I want is in the bottom position, and then I AND it with 1, and I have to leave that bit alone, which gives me 0, 0, 0, 31 zeros and a 1. So I can print out the third bit of any number now. I'm not sure why I want to do that, but I can find the third bit of -1 is 1. The third bit of 255 will be a 1. The third bit of 256 will be a 0. I've now got code that can give me the third bit of any number. Now someone's saying, have we seen the code of print bits? Not now, but you haven't yet, but oh, no, by the way, I use studint.h to get uint32. I've got prototypes for print bits and printbits.h. Let's look at, just out of curiosity, so let's look at printbits.h just to remind ourselves about multi-file C programs. Oh, interesting. It's actually it's quite a nice example of a multi-file C program. It actually includes student.h itself, because to define the argument type of print bits it needs uint64t. So we have an include file including another include file. So there it tells us print bits expects a unsigned 64. Now we're not going to get into it, but for complicated reasons we can supply values with less bits here, and C will automatically do an appropriate conversion for us. And also we're saying then how many bits we want to print. It's an interesting prototype, don't worry too much about that. Also here we're seeing a guard. I don't know if we use those in 1511. We probably should. It's really good programming practice. This is a way of ensuring that if an include file is brought in multiple times, included multiple times, we don't get an error. You're saying, well, why would you include an include file multiple times? The answer is when you have include files that include other include files, this can happen. And you'll see student.h is included here. That was also included back in the main in the main program. If I go back, I can go back. It was included here. So it's actually student.h is actually included twice into this program, once directly and once in printbits.h. This could produce an error. The C compiler could get upset saying you've defined uint32.t twice, uint32_t twice, except student.h will use the same trick to ensure it only gets included once. Don't worry about too much about that, but it's a standard C trick. All right, I guess let's get to the more interesting. Let's get to printbits.c, which has got some beautiful functions in it. So here is a function we've generalized. This is a function to extract the nth bit from a value. It says, give me a 64-bit value, an n, and I'll give you back the nth bit. First, I shift the value across n bits. You're saying, wait, you said it's only safe if value is unsigned, and I look back up here, value is unsigned, yeah. And then I throw away all but that bit I want, and then I return it from the function. So that's generalized the code we saw in my simple example. That's using shift and and to chop out an individual bit. So there really should be, it's not a well-documented function, is it? The crucial thing to document in a function is the possible values it returns. This function returns two possible values, 0 or 1. Poor coding, Andrew. Very poor coding. Similar function that prints the bottom how many bits of a number, and that just does it using this function. Is there better ways to do it? You could probably fold these operations, do it marginally faster. It wouldn't matter in this code. And a smart compiler could even fold these together, but we just, in order, print out, if we're asked to print out the bottom 8 bits, we print out bit 7, 6, 5, 4, 3, 4, down to 0. Now, if you haven't seen for loops before, you can ask in this week's tutor if it still hasn't to come. I think there was a tute question about for loops for people who've already gone through, but research it yourself. That's a good thing to get up to speed with. Read about for loops, how they relate to while loops. Maybe get if you've written programs with while loops last term in 1511 or earlier, and translate them to a couple of them to for loops, just to make sure you know what for loops are like. But that executes how many bits times, and each time it writes out 1 bit. I like that example. Beautiful code. Yeah, for loops and while loops are almost syntactically the same. Only when you get to break and continue is there a subtle difference related to this part here. A for loop without a break or a continue can be easily turned into a while loop. Now, that was lovely. Let me return to my lecture slides and see where we're up to. That's a right shift. Those are the various operations there. Yep, so get bitwise.c, run it yourself, put values in. Now, as I've said, you can't look at 23,032 and figure out how it turns into bits. Well, it's a complicated calculation that will be challenging for you to do in your head. But you can put in random values, or you can put in carefully chosen values that are close to powers of 2. Sometimes that's interesting, or small negative or positive numbers are also interesting. But experiment with values with this program, experiment with shifts, and make sure you understand you should, given the bit patterns, so given A, B, and C as bit patterns, everything else here should make sense to you. You should be able to do that in your head. You should be able to look at that and figure it out. So run this bitwise.c program. Now again, this translation of that binary pattern to base 10, again, that's a painful thing to do in your head. So, but you should be able to do in your head the translation to hexadecimal. So you should be able to get these values and translate this in your head, because you just chop it up into 4 bits and do that. So make sure you can do that. You've got to understand all of this. The next, in fact, the whole we will go through for the next 6 weeks is all depending on you understanding this sort of stuff. So get across it now. As in this week. You'll be using this stuff next week in next week's lab. No, that's the code to that. We've already seen that. Oh, shift as multiply. Let's have a look at the shift as multiply function. Don't tell me. Bear with me. In my prep for this, I didn't copy across. There we have it. Oh, a lot of code here, isn't there? Let's run the code, and then try to understand the various bits there. There's some good bits there to understand. So we want shift as multiply, and it's using that print bits.c, which we just got coded up. So we'll compile our 2-file program, and we'll put it in shift as multiply. There we go. This one takes a command line argument rather than scanf. And we'll certainly be doing that in a lot of exercises. Putting strings as command line arguments, turning them into numbers, and then playing with the bits of those numbers. So it takes one command line argument. So I put in, I don't know, 12. I think this program then prints out 2 to the power of 12. But let's find out. 4096 is 2 to the 12. And there it's all happening. But it doesn't do it with multiply, it's doing it with shifts. Let me show you one useful thing. You might not appreciate this yet. If you want to do lots of things in your head, lots of calculations in the head, and you're shifting base 10 to base 2, a very useful relationship is 2 to the 10 is approximately 10 to the 3. I don't know if you've taken physics, lots of physicists rely on doing lots of applied physics. People working with that rely on being able to do those sort of those approximate calculations in their heads to think about things. So if you're shifting between 10 and base 10 and base 2, 2 to the 10 is almost exactly 10 to the 3. Just a side note. Well, let's try that with a bigger number. So let's do 2 to the 30 Oh, there we go. What about 2 to the 31? Ah, very nice. So what else have I got in this program? It's getting n from the command line. It's created a uint variable there. Oh yes, there's a nice thing here. Let me show you. This looks a little weird. You're thinking, why has he written it like this? You're thinking, I can simplify Andrew's program. And you may well be able to improve my programs in general, but this is not an improvement. So that looks like that might be good code. Let's compile that. And run it. And say shift as multiply 31. Oh, we've got an error. But why? And the clues are here. Left shift of 1 by 31 places cannot be represented as an int. You're thinking, well, but what the hell? Power of 2 is not an int. It's uint 32, and it can represent it. This comes down to types. So this is one of my little life tips for you. Look left, look right when crossing roads. When was that? Was that first class you got taught that? Year 1? Another life tip I've given you is shifting. If you're shifting a value, it should be unsigned. You're saying 1, isn't that unsigned? What type is a 1 sitting in the text of a C program? Now if this was Python, we'd have introspection and be able to say, you know, ask it what the Python interpreter, what type is that? Sadly, we can't do that with C. C doesn't have introspection like that. There's no function we can give a value to and print out its type. But we can research this. We don't have to go very far. That 1 will be of type int. So there is a weird and scary way out of this. We can say to C, no, really it's unsigned, by putting a little u after that. Is that good? No, that's weird, ugly and scary, and I don't encourage it at all. But it works. There's another way using typecasts. Oh, I'll show you that as well. So I could say to C, look, turn this into a uint t. Take that 1 and turn it into this type. That's also an alternate way of forcing the transformation we need. But what I just recommend is the easiest, the least stressful way is put the 1 in an unsigned variable and then shift it. You can impress your friends by doing it the other way. Or, yeah, it can be when we well, actually no. If you're vaccinated and in a non-LGA of concern, you can go on a picnic with 4 other people, so you can discuss the 3 ways to do shifts safely and see at your picnic on the weekend, assuming you're lucky enough to be in a area without which is not where picnics are allowed. But this other than impressing people, this is what I recommend. Just put the value you want to shift in an unsigned variable, then shift it in a 2-step process. It's obvious it works. Let's walk before we can run. So that's showing you, yeah, shifting as a power of 2. Do we really care about that? Not really. And this code is not showing you how to calculate powers of 2 necessarily. If you needed them, multiplication is probably a better way to do it. This is understanding the consequences of these operations, understanding what's happening with the bits, thinking about this. If we know why this code works, then we know we understand the left shift operator more. Yes, if you can't impress your friends with your knowledge of C, you need new friends. That's what I'd say. All right, maybe that's not really true. Maybe you need friends who don't know C at all. But anyway, do I have anything more to say? I don't think I had any more thing to say about this, but I did have another example. I like 1 bits. How would I make a number of all 1 bits? It's a good question. How would I make lots of 1 bits? I'd like to print out, a program that I give it a number. We'll just take this example. This is getting n in. Change this so n 1 bits makes up a number made of n 1 bits. So I give it 3, it gives me a number that's 111 in binary. Give it 5, it gives me 11111. How would I do that? So it's not power of 2 anymore. It's 1 bits. That's what I want. 1 bits. Lots of 1 bits. So many 1 bits. I'm getting there. I'm still thinking about how to do this. I can see how to do it, I think, with a for loop. So let's try doing it with a for loop and see if we can make that work. Create a random variable. Actually not bad. Give us an example to show you a for loop. 3 parts to a for loop. An initialization, a condition, which is just like the condition on a while loop. Why isn't that shifting across? There we go. And a post loop step, typically an increment. So that's a for loop that executes n times with I taking the values 0 to n minus 1. Right. Here's my strategy. Yeah, I got a strategy. I'll initialize 1 bits to 0. Good. I want to set the bottom bit, and this is how I do it. What does an OR operation do? Let's refresh our memory what an OR operation does. Go back. An OR operation has bits that are set in either of the 2 values we're ORing. We say X or Y, we get a number that has bits set if the corresponding bit of X is set or the corresponding bit of Y is set. That's an OR operation. Got that in your head? All right. Now look at my code. Look at my master plan. I say whatever's in this variable ORed with 1. What's the pattern of a 1? It's 0, 0, 0, 0, 0, 0, 1. So that gives me whatever bit patterns in this number now with the bottom bit set. Oh, and my last bit is, there should be a shift 1. So I'll do this n times, setting n1 bits, and then I'll shift it across, set another bit, set another bit, set another bit. That's my master plan. I reckon this works. So 1 bits, print bits.c. There's probably someone in the chat saying you've got a syntax error, Andrew. What's it called? In 1 bits. There we go. No, I have to. Power of 2 there. In time size of.
Is there a chance this might shift 32 times?
I don't know. You're saying my code could have a bug?
No idea.
I'm not swearing that this code is correct. Wait a minute. We'll write out 32 there. Alright, let's see if I've got it right. Let's write out a number that's got, see if it works. This is my master plan. See if this code will set 5 1 bits in this number and tell us what that is. Oh, so close. Oh, that's given us a number with 5 1 bits is 62, but it's got 1 1 1 1 1 1 0. Oh, so close. Alright. So you think, if you're following on this carefully, how do I fix my program? It's meant to give me a number that's got 5 1 bits right at the bottom, but it's left a 0 there. There's a tiny change to my program. Oh yes, looking Halogen. Is that your real name? That's an interesting choice by your parents if Halogen is your real name. I guess it could be your choice as well. And we support you in your choice of a form of lighting as a name. Alright. Well, it's not just a form of lighting, is it? Alright.
Family of chemicals.
Indeed.
Family of elements, excuse me.
You can tell
Personally
I never
looking forward to meeting their sibling, Chalcedon.
You can tell I never studied chemistry. Alright. So I took Halogen's suggestion and they were right. The code has worked. Asking for 5 1 bits, this code, it sets the 1 bit, then shifts the bits across, shifts the 1 bit, shifts them across, and we finish up with 5 1 bits. Beautiful. That's pretty amazing. Let's be brave. Let's actually try some other values. Let's try 31 bits. That should be a big number. Eleven 1 bits. 32 1 bits. Does that actually work? Oh, n is too large. Huh. That should actually work. I think that should be allowed. Oh, yeah. It works for this, but it'll break from my strategy. There we go. Alright. So that's nice. That's a good example of sort of putting bit operations together. Alright. I'm a little worried that about some of you have been freaked out because I've used a for loop and you haven't seen for loops much at all. So let's change this to a while loop, just to show you how simple the transformation is. The initialization goes there, the for becomes while, and the last step, the I++ comes down here. And that's the same loop, just as a while loop, for old time's sake. Let me show you a different idea. Is there a better way to do this? To get that many 1 bits? Any thoughts? I can do it actually, I think, without a loop by being clever about bit operations. Can you? Alright, let me show you how you might do it without a loop. Let's put 1 in there. We'll shift it across n positions. That will give us a number that's 1 followed by n zeros. What happens if we then just subtract 1 from it? What does that do? And why? Let's try that out. It works. I think we need again to go to debugging. Let me emphasize again the importance of getting examples like this and debugging. It's unfortunate printf doesn't have a print bits operation. Maybe that'll get added in a future C standard. Would be quite nice. So let's put debugging statement in. We'll print it out there, there, and there. So 3 debugging printfs, and see what happens. Print out the bits 3 times. If we compile the program first, that will help. Print the bits. All right. There's my master plan. There's my, even make this larger. There's my secret plan. So I want 5 1 bits. First I put a single 1 bit in the number. There. Then I shift it across 5 positions. So in as 5, come in through the argument there. Shift it across 5 positions. Then I get this number, which is 2 to the 5. Now it depends on my knowledge of arithmetic. I subtract 1 and drop it down to the next number below, which is 2 to the n minus 1. 2 to the n minus 1 will contain n 1 bits. You can do a mathematical proof of that if you like, that 2 to the n minus 1 is 2 to the n minus 1 plus 2 to the n minus 2 plus 2 to the n minus 3, and so on. You can go away mathematically. You should, if this isn't intuitively obvious, you should go away and do the arithmetic until it is intuitively obvious what's happened here. But those are the 3 steps there. noting. Oh, except I've made a mistake here. That should be 1 bits shifted across to make sure it's on the side. There we are. So that's doing the shift across. This is not a curiosity. This is not. Oh, let's play with these and make get our feelings for these operations. It's actually quite useful to get values with a certain range of 1 set. I'd call this a mask, because then we can AND it with another value and just get the bottom, say 5. If we want the bottom 5 bits of another value, we can construct this and then AND it with the other value, and we're left with whatever the bottom 5 bits were of the other value. So this is a very useful technique. You'll see us using this a few times in upcoming weeks. Yeah, thank you, Zach, for that. Swapping that over to base 10. Yeah, as I said, get comfortable with this idea of different bases. It's a fun idea. You needed to know this anyway, just to understand the world. But why should everything just be base 10? So get comfortable with all these ideas. All right. I think that was nice. What should we've got time for perhaps a little bit more. What can I show you now?
I'll say that I can't put my finger quite on why we use base 10, but maybe that's just me.
All right. So pun of the day from Jashank. So it could be our toes, that lie at the foot of it. There you go. Oh, that's probably not as funny as yours. Oh, okay. So what about we want a certain range of bits? Let me show you that as well. There was one more thing I wanted to point out before we went to that. A couple of things about this program. Note the robust programming, checking we got the right number of arguments, printing a message to std. Don't worry too much about that. We'll talk about streams in week 7, I think it is. But printing a message and we'll see exit status. So yeah, so foreshadowing. Come week 7, we'll explain why we do both of those things. Also, strudel. I didn't mention this function. Strudel. Alright, it better be on my machine. I'm a bit disappointed my machine didn't have limits.h, but it better have strudel. Pull up a manual entry. Oh god. Yeah, that's what I mean. Manual entries, they're a bit terrifying. Alright, you've got to sort of get brave with manual entries. There's stuff there that you're just never going to understand. I mean, what does this mean? I mean, you're going to have to skip over stuff you don't mean to try and get to the stuff that you want in manual entries. And if you figure out strudel lets you specify the base of the number. So strudel, you give it a string, a pointer to a character string as its first argument. Strudel has a simple friend called, I guess, a to I, that just converts a base 10 number from a string to an integer, which we might have used in another course. Strudel is much more powerful. You give it a string. In this case, it's a word from the command line, a char star. It gives you back a long, which we can put in an int. Don't worry too much about that. You let you specify the base, but wait, there's more. If you specify a base of 0, strudel will accept hexadecimal if you put a 0x in front of it. So that lets us specify hexadecimal constants to be converted. And we'll actually use this in lab exercises. Don't worry, this is code we're going to be giving you, not code you'll have to write. But it's best to understand these things. Strudel also has the possibility of giving you error checking that it actually managed to convert the string to a number. If you supply a non-null pointer here, you can check whether the conversion succeeded. I'm lazy here, I'm just saying, no, I'm not going to check. But I am taking advantage of that, letting me specify. Oh, that's quite nice. So I could actually try, let's try that out. Let's demonstrate that before we go on. It's sort of nice. So I can put a hexadecimal constant here. I can put 0xe, and I'll get a number that's got e bits. E is 14 base 10. I'll get 14 bits. So that's Strudel taking both base 10 and base 16. If you put a little 0 hex in front of it, as you can do in C programs, it says, oh, that's base 16. There will be lab exercises where we want to write code that you pass. It's more convenient to put hexadecimal constants there because you can understand what their bit pattern looks like. So we'll use Strudel just for those reasons. Don't worry about that too much. That's all this stuff I've just talked about. Side note: this notion here of shifting and subtracting. This was the core message. Alright, I can go one further. How about I want a certain bit range set rather than just the bottom 5 bits? Maybe I want bits 7 to 11 set. Can I write a program to do that? And the answer is I can. I think we're running out of time, so I'll show you. We'll finish by showing you that program. I'll copy it over. I've got it here. Copy it over and show it to you. The program is called setBitRange.c. Sorry, bear with me. There we go. We'll come back to this. We'll recap this little bit and then go to extracting various parts of a number in the next lecture. So here I'm getting a low bit and a high bit, and I want to create a value that all the bits, low bit to high bit, are ones. Everything else is a 0. All the values apart from that are low bit to high bit. I'm calling this value mask because that sort of in English is what the purpose of what we're going to use things like this for in future. Let's try it out. Yeah, it's actually a nice combination for this lecture. So let's try this out. DCC setBitRange.c, and it has to have printbits.c as well. Let's try that out. Alright, so let's set bits. It's low, so let's set from bit 4 to bit 24 to be ones. Yeah. Are those values inclusive or exclusive? Good question. That would be a good thing to document in your program, wouldn't it? And apparently the first one is... Oh no, they're both... Are they both exclusive? No, the second one's exclusive. There we go. That's probably the one I want. So I've now got code that can create any set of any range of specify any range of values, 25 to 29, 1 to 11. I can create values with ones in any position. The purpose of this is when I want to pull out parts of a bit pattern. we're going to use this a lot when we get to understanding floating point numbers. Alright, we're at 3 minutes to the hour, unless there's some commentary from Zach, Jashank or Dylan via the chat or otherwise. I think we're going to say goodbye for today, and next week's lab exercises will get really into the course content, as will the tutorial. So, but we'll have one more lecture before that. So we'll be back to talk more bit operations and doing more interesting things with bit operations. So make sure you understand everything we've seen, because we're trying to do some quite clever things with bit operations, and then it's off into understanding the bits not of an integer but of a floating point number. Alright, so thank you all for coming in. I hope you got something out of this lecture. The other thing I'd say is there's lots of resources online. We've linked some to the class webpage. You find anything better, let us know, and we'll also link them in. So there are other explanations of this, but yeah, you've really got to understand everything we've talked about today, apart from me sort of chatting about strudel L. You've got to understand all what's happening with these bit operations. So from last lecture, you had to understand everything that was happening with bases and binary. This lecture, you've got to understand everything that's been happening with the bit operations. Alright, so thank you very much for your attention. Thank you, Zach, Jashank and Dylan for your comments. But I'll sign out for now and talk to you next Tuesday at 10 AM.